If you live in a cold climate, then you probably have a natural gas furnace to heat your home. Modern furnaces are efficient, converting 95% of the fuel energy into useful heat. But did you know that your furnace is more efficient than a high-tech furnace in an oil refinery? With over 100 years of improvements in the oil refining industry, why are refinery or industrial furnaces hardly ever better than 85% efficient? It's time for the truth. A furnace has two sides, not a left side and a right side, but a hot side and a cold side. Hot air from the house at 20 degrees Celsius is pulled into the cold side by the fan. The fan then pushes the air up and forces the air past the heat exchanger. This warms the air to 40 degrees. The air is sent to different rooms in our house and keeps everything nice and warm. Now for the hot side. The hot side starts with natural gas, which comes in from the 1-inch black iron pipe on the left side of the furnace. Combustion air is pulled in from the room. A high-efficiency furnace has a separate air duct that delivers fresh air straight to the combustion chamber. Then we get fire at about 2,200 degrees. We follow the hot gas upwards from the flame into the heat exchanger where we recover useful heat for our home. Hot gas blows through the inside of the heat exchanger piping and cold air is blown past the outside. The cold air gets warmer and the hot gas gets colder. This simple bit of piping defines the efficiency of our furnace. Let's take a look at efficiency to understand exactly what it means. Efficiency is defined by the amount of useful heat that we could recover compared to the amount of heat that we could recover theoretically if we burned the fuel with the perfect amount of air, cooled all of the combustion products to an arbitrary 15 degrees Celsius, and condensed every molecule of water into liquid water. This graph shows us how efficiency is related to the stack temperature, the temperature of the hot, which is the temperature of the hot gas after the heat exchanger. And we can see that if we recover no heat, we will have our flame temperature of 2,250 degrees. Let's zoom in on the region of interest for furnaces. Water vapor starts to condense at about 60 degrees Celsius. And this provides a fair amount of heat. The utilization of this heat was the prize in the 1990s when residential furnace efficiency was increased to 95%. Efficiency only depends on the stack temperature. That's it, period. There is a minor difference between coal and natural gas, but not enough for us to consider here. Then, what is the reason why a refinery furnace has such a low efficiency compared to a residential furnace? Well, for that, we need the second law of thermodynamics. And no discussion of the second law is complete without mentioning the French military engineer and physicist Sadi Carnot. Carnot was doing work in 1824 to see if there were theoretical limits to the efficiency of steam engines. But it is this rather stern-looking guy, Rudolf Clausius, who applied some mathematics to the principles of heat and concluded that heat can never pass from a colder to a warmer body without some other change connected therewith occurring at the same time. Which means your nice warm house loses heat when it's cold outside. Or your warm house cannot get warmer by extracting heat from the cold air outside. This is why we need a furnace to keep our house warm. It's pretty obvious. Our furnace burns natural gas with air and produces a 2,200 degree flame. The hot gas enters the heat exchanger. Cold air is fed to the cold side of the heat exchanger and warms up to 40 degrees. The second law of thermodynamics states that the flue gas can never drop below the cold side temperature of 20 Celsius. Our house furnace cools the gas to 40 degrees, and voila, this means that our furnace is 95% efficient. But a refinery furnace is not warming up air at 20 degrees. The cold side of the furnace is crude oil at 130 degrees. And let's be fair and design the heat exchanger so the hot side approaches 20 degrees to the cold side temperature. So that would be a flue temperature of 150. And voila, this says that our refinery furnace must be 85% efficient. The efficiency of a furnace depends on the temperature of the cold feed, and this determines the stack temperature. Refinery furnaces are less efficient than residential furnaces because refinery feed is at a higher temperature compared to keeping a house at 20 degrees Celsius. The refinery does not have a stream at 20 degrees Celsius where we can recover the remaining heat from the 150 degree flue gas. That is why a refinery furnace has a lower efficiency than a residential furnace. Is there any way to improve this? Stay tuned.